And 2, and we are going to be dealing with vectors. In fact, our vectors will be dealing with x, y, and z. And also, we're going to review everything pretty much that we had learned with vectors with x and y. The first thing that we're going to look at is the component form, some of the forms that we're familiar with. So vectors in space can be modeled by ordered triples of the form. So vector v is v1, v2, v3. Or in standard unit vector form, which is v1i plus v2j plus v3k. So you can see here we are adding to our vectors this third component. Here, these are each unit vectors. So this is the unit vector I, unit vector j, unit vector k, and the zero vector. All right, now let's look at the component form. Component form of a vector is the difference between the endpoint and the initial point. So if V is represented by a directed line segment from P to Q, so we're going vector P to vector Q, then we are going to take and subtract Q1 minus P1, Q2 minus P2, Q3 minus P3, and that would be our vector in component form. Let's try this. The component form of this vector from 2, negative 4, 1 to 5, 7, 0. So component form would be 5 minus 2, 3, 7 minus negative 4, 11, 0 minus 1, negative 1. Oops. There you go. All right, if the terminal point of the vector is 1, 3, 5, the terminal point of vector 1, 3, 5 is 2, 5, 8, what's the initial point? Well, here's what we know. We know that Q, if this is vector Q right here, minus P is equal to 1, 3, 5. That's what we know. And we know that Q is 2, 5, 8. So by what are we subtracting here to get 1, 3, 5? That's what we're trying to find. Well, 2 minus, so the vector that we're trying to find, the initial point P, is 2 minus what is 1, so 1. 5 minus what is 3, so 2. And 8 minus what is 5, so 3. So there's our final answer to that. So that's how you work with component form. The next thing that we're going to look at is just kind of looking at comparing two vectors. Two vectors are equal. They're considered to be equal if and only if their corresponding components are equal. Because if the components are equal, then their magnitude would be equal and they'd have the same direction. All right, magnitude. So magnitude, again, we're just adding this last component to it. This should be a power 2. We would have the magnitude of a vector is you take the component form and you square each of the 3 parts, add them together, and then take the square root. Remember that these are already parts that have been subtracted and in component form. So you square them, add them together, and then take the square root. That will give you the strength or the length of the vector. So in example 1, we have this vector. It was already in component form. Now what we're going to do is we're going to find its magnitude. So the magnitude would be 3 squared plus 11 squared plus negative 1 squared. This would be equal to 9 plus 121 plus 1, or the square root of 131. Okay, so if this is vector v, then this is the magnitude of vector v. All right, now we're going to look at the unit vector. A unit vector is a vector that is of length 1, and we can find it by using this formula. The unit vector is the original vector divided by its magnitude. Vector divided by magnitude. So looking at this example, example 3, if we want to take the vector v, again, which is 3, 11, negative 1, and find the unit vector to that, then it's going to be 3, 11, negative 1 on top. And we're going to divide that by its magnitude. Well, the magnitude was 131. So we're looking at 3 over the square root of 131, 11 over the square root of 131, and negative 1 over the square root of 131. Or, if I rationalize this, then this is 3 square root of 131 over 131. All of these now are going to be rationalized. 11 square root of 131 over 131. And finally, negative square root of 131 over 131. So this is the unit vector. You take the vector, you divide it by its magnitude, and then simplify. All right, to add two vectors together, we need to add their corresponding components. So just adding basically like parts. So you're going to add 6 plus negative 5, 1. Add negative 4 plus negative 3, negative 7. And add 2 plus 3, which is 5. Subtracting vectors would be the same. You just follow the operation. You just have to make sure that you match up their corresponding parts. Scalar multiplication of a real number and a vector. It's like the distributive property. So you're going to take C and you multiply it by all the parts. Here you can see that C has been multiplied. So this would be C times U3. So I'd have 4 times 3, 12. 4 times negative 4, negative 16. And 4 times 5, 20. And there you have it. All right, now we're going to look at the dot product. So again, the dot product, we have the original set here, but now we're going to add the third component. If the dot product of two vectors is 0, then the vectors are perpendicular to each other. So here again, you have vector u, which is u1, u2, u3, and vector v, which is v1, v2, v3. So we're going to multiply u1 times v1, u2 times v2, u3 times v3, and you add them all together. Now if the dot product is 0, then the vectors are perpendicular. Vectors are parallel if they are a scalar multiple of each other. So really we can tell there by just finding ratios. And points are collinear in space if their vectors are parallel to each other. All right, let's look at the next example. Find the dot product of uv. So again, we're going to multiply negative 1 times 0 plus 4 times negative 1 and negative 2 times 5. This is 0 minus 4 minus 10. The dot product is negative 14. All right, in the next example, we have to show here that the vectors are parallel to each other. There's a couple ways to do that. Again, so we've got 2, 6, and 1 for one vector, and the other vector we have is 10, 30, and 5. One thing that you can recognize is to get from one vector to the other, you're just multiplying by 5. However, if you didn't know that, you can just do ratios. 2 to 10 is the same as 6 to 30, which is the same as 1 to 5. So one is a multiple of the other, so they are parallel. Because each one of these equals 1/5. Show that the points P and Q and R are collinear. If these points are collinear, P, Q, and R, then what we would know is the vector from P to Q would be parallel to the vector from P to R. They'd be parallel to each other. So let's find vector PQ. Vector P to Q would be component form. 3 minus 1 is 2. 2 minus 3 is -1. And 7 minus 4 is 3. Vector P to R. Component form. 5 minus 1 is 4. 1 minus 3, -2. And 10 minus 4 is 6. So you can see here that if I just multiply PQ, so 2 times PQ is equal to PR, which means it's a multiple, so they're parallel to each other. And if they're parallel, then they're collinear. All right, the last thing that we're going to look at is finding angles here between two vectors. And I think I'll go ahead and stop this video so that we can, the last couple problems dealing with these angles and maybe an application problem we'll see on the next video.